My name is Chandrakana, and today I will talk about a tool for synthesizing parametric 3D models using e-graphs and a new technique called inverse transformations. Designing physical objects is programming. I'm sure many of you have heard about democratized manufacturing techniques like 3D printing that aim to empower everyone to be able to make and build their own things. A key component of this promise of democratized manufacturing is flexible programmatic design. As an example, consider here the design of a ship's wheel and a parametric program to represent it. As you can see, having this parametric program lets us customize the model and get different designs very easily. Unfortunately, models are rarely shared as parametric programs. Instead, they're typically shared in a low-level triangle mesh format that makes editing impractical. So recently, several tools called mesh decompilers have emerged that try to solve this problem by decompiling meshes into straight-line code that captures the geometry of the design. The outputs of these mesh decompilers are in a language called constructive solid geometry. Constructive solid geometry supports 3D primitives like cylinders and cuboids, affine transformations like scale, rotate, and translate, and binary operations like union, difference, and intersection. One problem with mesh decompilers is that they do not expose any high-level structure in the program. For example, in case of this ship's wheel, the flat program does not capture the repetitive pattern of the spokes. This makes these straight-line programs difficult to work with, especially for large, complex models. So in this work, we propose a solution to this problem by presenting a tool, Salinsky, that automatically infers loops from straight-line programs. Salinsky takes as input a flat 3D CAD model and generates an equivalent parametric model in a language called CAD. CAD supports 3D CAD features and also functional programming features like folds, maps, and tabulates that can be used to represent loops. The parametric programs that are synthesized by Salinsky can be easily modified to get different 3D designs. So at a high level, Salinsky is a tool for automatically inferring loops from straight-line code using functional programming features like folds, maps, and tabulates. Now, to see how Salinsky works, we will first consider an ideal input where the program happens to be organized in a way where it's easy to see how to convert it into a loop. Later, we will show how Salinsky handles more general cases. Salinsky's core strategy is based on term rewriting. So here we have a program for the ship's wheel where a cylinder is unioned with an inner union of rotate expressions. Salinsky uses a syntactic rewrite to convert that inner union into a fold expression with a union operator and a list of rotate expressions. Then it uses an algorithm called structure finding to separate out the parameters of the rotates from their CAD arguments. The structure finding algorithm can be applied more than once, and after that, Salinsky uses a custom solver to find a closed form arithmetic expression to represent the parameters that were separated out by the structure finder. Finally, Salinsky uses a few more syntactic rewrites to simplify the program further. In this talk, we will focus more on the structure finder and the custom solvers. Salinsky's structure finding algorithm searches a program for a list of expressions which use the same operator, and it separates the parameters from the CAD arguments. So for example, here, we have a list of rotates from which the structure finder separates out the list of the parameters of the rotate in list 1 and the CAD arguments in list 2. Both these lists appear under a map2 expression which applies the operator rotate to the ith element of the first list and the ith element of the second list. And as I mentioned previously, the structure finder can be applied more than once. So for example, here, it also applies to the second list under the map2, which is a list of translates. So once the structure finder separates the parameters from the CAD arguments, Salinsky uses custom solvers to find an arithmetic closed form to represent the parameters in a more compact way. This is the high-level algorithm of Salinsky, but note that this is how it works on idealized inputs. Unfortunately, inputs to Salinsky are rarely ideal. And this is because they're machine-generated, either from mesh decompilers that return flat programs, obscuring the overall structure, or from compilers of interactive CAD tools, which also do not guarantee that they will be ideal. So here is a comparison of the ideal input that we have so far seen with an actual input for the ship's wheel. So in this actual input, no op subexpressions such as rotation by 0 may be omitted, expressions may appear in arbitrary order, and semantically equivalent expressions may be written using syntactically different forms. So due to these idiosyncrasies in the inputs, the previous rewriting workflow cannot be applied directly. So in order to handle these actual inputs, Selinsky must interleave the strategy we have seen with CAD axioms that can be used to line up the sub-expressions. However, imposing a specific order of interleaving can prevent profitable rewrites to be applicable in the future. And this is known as the phase ordering problem in compilers. Selinsky avoids the phase ordering problem by using a data structure called E-graphs. E-graphs have been shown to mitigate phase ordering by simultaneously applying a set of rewrites in all possible orders without forgetting any previously discovered expressions. This makes E-graphs a really efficient data structure for representing large numbers of equivalent expressions. So let's see how Selinsky uses E-graphs for applying CAD identities. Here we have two expressions that are semantically equivalent but syntactically different. Initially, the E-graph only has the AST of the input expression. In this data structure, the gray boxes are called E-nodes, which correspond to operators in the language, in our case CAD, and the dotted boxes are called E-classes or equivalence classes that represent sets of equivalent expressions. The edges connect an E-node to an E-class of its children. After the rewrite rule fires here, the E-class of the rotate expression is populated with the equivalent scale expression, and a new E-class is introduced in the E-graph that contains the parameter of this new scale expression. So this gives us an idea of how Selinsky uses an E-graph to store a large number of equivalent expressions that are obtained by applying syntactic rewrites, including CAD identities, to the inputs. Now let's see how Selinsky integrates the structure finding algorithm and the custom solvers in the E-graph. So here, we again have the list of rotate expressions under a fold union. Selinsky applies the structure finder, and as a result, a map2 expression is introduced in the E-class of the concrete outer list of rotates. The map2 has three children: the rotate operator, a list of its parameters, and a list of the CAD arguments. Selinsky then inspects the E-classes to find the parameters and sends them to a custom solver. An advantage of using the structure finding algorithm is that now the solvers only need to deal with flat lists of parameters, and they do not have to worry about the overall CAD structure because the structure finder separates them. So in this case, the solver finds an arithmetic closed form that can be used to represent the list of parameters more compactly. And then it introduces a tablet expression back to the E-graph. Note that this tablet expression is equivalent to the list of concrete parameters. And what that means is that this tablet expression will be unified with the list. In other words, it will be in the same E-class as the list of parameters. One thing to note here is that this worked out because the list of parameters were all in the right order for the solver to find this tablet expression. But recall that in actual inputs to Selinsky, expressions may appear in arbitrary order. For example, here we have the ship's wheel program, but in this case, the rotates are not sorted based on their parameters. So looking at the E-graph for this program, we will notice that the strategy that we just saw cannot be directly applied because the parameters of rotate are not sorted. What this means is that for the solver to find an arithmetic closed form, the solver must first sort this list of parameters. However, sorting the list of parameters and then finding a tablet expression indicates that this new tablet expression is no longer equivalent to the original list of parameters. And this is because reordering a list does not preserve the meaning in this context. So we cannot unify this tablet expression with the list of original parameters. So how do we solve this problem? One naive solution is to add all permutations of the list in the E-graph. However, this has two problems. First, now there are exponentially many expressions in the E-graph, which is known as the AC matching problem in the SMT community. And second, our rewrites now need a lot more context to know when a permutation will preserve meaning and when it won't. So instead, Selinsky uses a new technique to mitigate the AC matching problem called inverse transformations. The key insight of inverse transformations is that Selinsky allows its solvers to speculatively transform their inputs in order to allow for more profitable rewrites in the future. In return, the solvers are required to undo the transformation before introducing an expression back in the E-graph. So let's look at an example to understand it better. So here we have the input where the rotates are arbitrarily ordered, and our goal is to find a program where there's a tabular expression instead of this list of rotates. So as we have seen before, Selinsky applies the structure finder to separate out the parameters of the rotates from the CAD arguments. At this point, the E-graph shows a map to expression in the same E-class that has the concrete list of rotate expressions because they're equivalent. And then Selinsky sends the list of vector parameters to a custom solver. Note here that since the parameters are in an arbitrary order, the solver must sort the list first in order to find the tabulate. But as we just saw, this tabulate is not equivalent to the original list, and therefore this unification of the tabulate with this list is not sound. But that was before we had inverse transformations. Now that we have inverse transformations, the solvers can actually be allowed to transform their inputs however they want. And in this case, the solvers end up sorting the list to find the closed form. The key idea, though, is that in return, the solvers are required to annotate the expressions they find with an inverse transformation to undo the transformation and restore the equivalence. In this case, the inverse transformation is an unsort, which contains the permutation with which the solver rearranges the input list. This ensures that the equivalence of that the solver broke by sorting the list is now restored by inverting the transformation. So from the E-graph's point of view, what this means is that now a new unsort expression is introduced in the E-graph, and crucially, the original list of parameters is unified not with the tablet expression, but with this new unsort expression, which wraps the tablet expression. Now, since the solver undid the transformation with this unsort expression, this unification is now back to being sound. Another advantage of using an E-graph can be seen here. So the solvers don't actually necessarily need to perform the most optimal transformation on its inputs. In fact, the solvers can actually try multiple transformations on the inputs, all of which can be efficiently stored in the E-graph data structure. So this is yet another advantage of using E-graphs. So now we have a new expression in the E-graph, and this expression is annotated with this unsort transformation. Selinsky provides rewrites that can propagate and eliminate these inverse transformations in order to get to the final output. So one such rewrite wraps the map to expression with an unsort sort. Both of the unsort and the sort here use the same permutation provided by the solver. Note that this rewrite is effectively a no-op because sorting and unsorting a list with the same permutation doesn't change the list. However, it does let Selinsky sort the original outer list, which is in the same E-class as the map2. Let's look at the E-graph to understand this better. So here we have the E-class with the map2 and the outer list. And now, in the same E-class, an unsort expression is also added. And this unsort points to the permutation that we found from the solver, which is the permutation the solver used to find the tablet expression as well. The other child of this unsort is a sort expression, which again points to the same permutation that we found from the solver. The other child of this sort is actually the E-class that contains the outer list and the map2. And what this means is that this sort transformation can be used to sort the outer list, which is equivalent to the map2. And this facilitates the structure finder and the custom solver of Selinsky to apply on the sorted list as well. And the good news is that this time, they will successfully find a tablet expression without having to further transform this list because it's already sorted. So now, all we are left with is this unsort transformation. Another good news is that this transformation appears directly under a fold union, and a fold union is invariant to list order. Therefore, a syntactic rewrite can be used to eliminate it, giving us the final parametric program. So in this way, inverse transformations allow for flexible integration of solvers with an E-graph-driven rewrite system. Some of the transformations we have implemented for Selinsky are permuting lists and partitioning lists and converting between Cartesian and spherical coordinate systems. However, we believe that this technique of inverse transformations is more general, and it can be used to overcome AC matching in other settings as well. So, so far we have seen several rewrites, including custom solvers. And Selinsky applies all these rewrites to the input expression until saturation, and then it uses a cost function, typically AST size, to extract the best program from the E-graph data structure. Selinsky is implemented in Rust in about 2,000 lines of code. It has about 65 rewrite rules. Our code is publicly available in this repo. And Selinsky uses an egraph library called Egg, which is developed by my co-author, Max. You should talk to him if you're interested in using Egg for your application. Now let's discuss some results of using Selinsky. We performed an end-to-end evaluation of Selinsky, where we composed it with a mesh decompiler called Reincarnate. We found that Selinsky was able to significantly compress the inputs by finding loops in the flat programs generated by Reincarnate. We also ran Selinsky on the outputs of other mesh decompilers, and you can see the results in our paper. We also evaluated the scalability of Selinsky. To do this, we took about 2,000 customizable models from Thingiverse, a popular model sharing website. We first flattened these programs using a CAD compiler and removed all the loops, and then ran Selinsky on them to recover the loops. Selinsky worked on all of them and found the optimal programs within a second for all of the models. Here are some example programs synthesized by Selinsky, demonstrating the types of loops it can infer. So to summarize, we presented Selinsky, a tool that can automatically infer loops from flat programs using egraphs, and a new technique called inverse transformations. Thank you.